Okay, question 3. So for which value of A does the matrix M have an inverse? Well, the inverse is 1 over the determinant multiplied by a new matrix. So that'll work as long as the determinant is not 0. So we need to find the determinant of M first. So the determinant of M, and that's found by multiplying first of all 2 by its minors, which is the matrix here, using the determinant of AD minus BC. So that times that. So we start with 2 times minus 1 times minus 1, which is 1, minus 1 times 2, which is minus 2. Now for the middle term on top, it's a negative coefficient, so it's minus A multiplied by its minor. Now the minor of A is found by eliminating that row in that column, so you're left with 1 times minus 1, which is minus 1, minus minus 1 times minus 1, which is positive 1. And then you return to the minors for the value of 4. So there's the value of 4, so we cross off that, so it's plus 4 times 1 times 2, which is 2, minus 1 times minus 1, which is 1. Let's evaluate what that actually is. So 2 times 3 makes that 6. Minus 1 minus is minus 2a, minus 2a is plus 2a, and 2 take 1 is 1 plus 4. So the determinant of this is 10 plus 2a, but it would normally be 1 over 10 plus 2a. However, if it's 1 over 10 plus 2a, it's the determinant of M, 1 over 10 plus 2a. So when is this have an inverse? It has an inverse as long as this is not 0. So 10 plus 2a is equal to 0 means that 2a is minus 10, so a is minus 5. So as long as a is not equal to minus 5, it has an inverse. So for which values of a? It's when a is not equal to minus 5. Okay, next one. Given that it's non-singular, singular meaning it has no inverse, so that case, find m minus 1 in terms of a. So m minus 1 in terms of a, we now have to actually do the inverse. So there's quite a few steps here, so I'll do that a bit further down. There we go. Okay, first of all we have to do the matrix of minors. Now the matrix of minors is all of the minors, but you don't have to multiply this time by the coefficients on top. So the first minor you get for the top left is the one we've already done, which was minus 1 times minus 1, take away minus 1 times 2. So if you do that, I'm going to write it out in full. So it's minus 1 times minus 1, which is 1, minus 1 times 2, which is minus 2. Okay, that's the top left value. Then you do it again for the one in the top middle, but this time you don't include the a in front, or the negative. So it's 1 times minus 1, which is minus 1, minus 1 times minus 1, which is 1. And then the one for 4, which is these ones, which is 2, minus, and minus 1 minus 1, or minus 1 times minus 1 is 1. Then for the middle row, now you're doing the minors for this one, which means you're eliminating this and this. Therefore it's now a times minus 1, which is minus a, and 4 times 2, so it's minus 8. And then when you do it for the next one, for the middle centre, you're now going to have 2 times minus 1, which is minus 2, minus 1 times minus 1, which is minus 1. Okay, for the next one, we've got, oh sorry, I've done 1 times minus 1, I meant to do 4 times minus 1. Hold on a second. So it's minus 2, and 4 times 1 is minus 4. Minus 2, minus 4. Okay, and then the next one, you're doing this on the middle right, so you're going to get rid of that and that. So it's now 2 times 2, which is 4, minus a times minus 1, which is minus a. And down here, we've got bottom left in a similar sort of way, so it's this we cross out, so it's a times minus 1, which is minus a, and then it's minus 4 times minus 1, which is minus 4. I'll stop doing this now for the middle, so it's going to be 2 times minus 1, which is minus 2, and then 4 times 1, which is minus 4, and finally bottom right, which is this one, so it's 2 times minus 1, which is minus 2, and a times 1, which is a. Okay, so that's the matrix of minors. We'll just simplify that. So that will be 3 minus 2, 1, minus a minus 8, we can't do anything with, 2, 4 plus a, minus a plus 4, minus 6, and minus 2 minus a. Okay, so that's your first step. That's the matrix of minors. Let me scroll down a little bit. Okay, having done that, we now swap signs in certain positions. So if I change colour, yeah, that should do it. Okay, so we're swapping signs. So when we swap signs, we swap the signs not in the leading diagonal, just in the positions that are here and here and here and here. So we're swapping the signs with those values. So when we do that, we end up with this new matrix. So we end up with 3, 2, 1 with positive a, positive 8. 2 stays the same, minus 4, minus a, and that stays the same, and you get 6, and that stays the same. Okay, so that's now the signs swapped over. After you swap the signs in those positions, you're now going to transpose the matrix. So the leading diagonal stays the same, but if it was going 3, 2, 1 across, it now goes 3, 2, 1 going down. So we're now going to transpose the matrix. Okay, so that's now the matrix transposed, which will be going across is now 3, a plus 8, and minus a plus 4. So what was going down is now going across. What was going across is now going to go down, so that's 3, 2, 1. The diagonal remains the same, and this minus 4 minus a is now going to swap with the 6. So it's minus 4 minus a, and it's going to be a 6 there. Okay, so that's the transpose matrix. And finally, we then multiply by the determinant, which we found 1 over the determinant. So we end up with the answer of 1 over 2a plus 10 from earlier, multiplied by this matrix here. And that's your answer for part B. Okay, moving on. The induction process. There we go. So we've done A and B. Part 2. Prove by induction. Now, when it's proved by induction, there's certain things you have to do. I'm going to rewrite the question because it's a bit hard to see from over there. So it's proved by induction that 3, 0, 6, 1 to the power of n is equal to 3 to the power of n, 0, 3 times 3 to the power of n minus 1, 1. And we have to show by induction that's true. So for step 1, we show it's true for n equals 1. So let's prove it's true for n equals 1. Put 1 in. So put 1 into this side is 3, 0, 6, 1 to the power of 1, which is just 3, 0, 6, 1. And on this side, we put it in, so it's 3 to the power of 1, 0, 3 times 3 to the power of 1 minus 1, 1. And if we think about what that is, it's the same as 3, 0, 3 to the power of 1 is 3, take 1 is 2, 3 times 2 is 6, 1. So you say it's true for n equals 1. Step 2 is to assume it's true for n equals k. So we're going to assume it's true for n equals k, which means we're allowed to use that 3, 0, 6, 1 to the power of k is equal to 3 to the power of k, 0, 3 times 3 to the power of k minus 1, 1. Now we've got to try and demonstrate it's also true for k plus 1. So we now have to prove it's true for n equals k plus 1. So if we do that, we're going to get 3061, but now we're going to use k plus 1. And if it's true for k plus 1, we should have exactly what is on this side, but everything should be replaced by k plus 1. So we actually know what answer we're looking for. We're looking to get the answer 3 to the k plus 1, 0, 3 times 3 to the k plus 1, minus 1, 1. We're looking to get that. That's our answer. So to do that, it's 3061 to the power of k plus 1, which is the same as saying 3061 to the power of k times another 3061. So we have to multiply these out. So we know what 3061 to the power of k is. That was there, which is written like this. So this matrix on the left can be rewritten as the one above. So it's 3k, 0, 3 times 3 to the power of k minus 1, 1, multiplied by 3061. Okay, so if we do that, we're going to get, as you go across, you multiply down. Let me scroll down a bit. There we go. So first step is we're going to get 3 to the k times 3, so that's 3 times 3 to the k, plus 0 times 6. So go across, you go down, so that's just 3 times 3 to the k. For the top right value, we want the top row by the right column, so it's 3 to the k times 0, plus 0 times 1, well that is 0. Okay, for the bottom left, so it's bottom times left column, so it's 3 times 3 to the k minus 1 times another 3, which is 9 times 3 to the k minus 1, plus 1 times 6, plus 6. Then we've got the bottom with that one, so we've got 3 times 3 to the k minus 1 times 0, which is 0, and 1 times 1, which is 1. So far we're at this stage. Right, now finishing this off, we have to sort of hopefully show this is equal to what we wanted earlier. Now, the top value of 3 times 3 to the k can be found by just increasing the power by 1. So that's 3 to the k plus 1, which is great. And that's 0, which is great. That one's 1. The only issue we've got is trying to make sure this load of stuff here can be written in the form we had earlier, which is that. Okay, so let's have a look and see if we can do that. Now, we want it in the form of 3 times 3 to the k, so I'm going to rewrite that as 3 times 3 to the power of 3k minus 1, like that, and then have the plus 6 at the end. Now if I expand that, we're going to get just this bit, in here and here. 3 times 3 to the k plus 1 minus 3, still plus the 6. Then, if I expand in again, we're going to get 3 times 3 to the k plus 1 minus 9 plus 6. And no longer is that bracket there. I just did that bit. And that's the same as 3 times 3 to the k plus 1 minus 9 plus 6 is minus 3. And now you can factorise out the 3 and say 3 to the k plus 1 minus 1, which is as we had earlier. Yes, that bit there. So, we've shown that if it's true for k, it's true for k plus 1. We've also shown it's true for 1, therefore it's true for 2, and if it's true for 2, it's true for 3, and so on. So we can say that by induction, it's true for n equals 1 and for n equals k plus 1, therefore true for all k. Okay, Next one. Question 4.